Hello, I'm Richard with EV4U. In this video, we will discuss DC circuits for an off-grid power system as well as backup generators. In previous videos, we discussed solar arrays and solar charge controllers. We showed a scenario where there was not enough solar input or battery capacity to keep up with the energy demand. That's when you might want to use a backup generator. Fuel power generators and inverters are commonly used to back up solar. As I mentioned in a previous video, generators are commonly powered by gasoline, propane, diesel, natural gas, or combinations such as gas and propane. Fuel-powered inverters are typically preferred over generators for small applications due to their greater fuel efficiency, lighter weight, smaller size, and quieter operation. Inverters also produce a much cleaner and higher quality electrical output, which is beneficial for appliances and electronics that are sensitive to power fluctuations. The size of the generator or inverter will depend on the amount of power you need. Add up the largest number of watts you'll be using at any given time and then add 20%. For example, let's say you need 1500 watts to run your computer and microwave at the same time. So you take the 1500 watts and add 20% to that, which would be 300 watts. So 1500 watts plus 300 watts would give you a total of 1800 watts. So like a 2000 watt generator inverter would work for that application. Remember, if you'll be charging your battery pack as well as powering your AC loads, add in the power required to run the battery charger or the converter also. We will discuss battery chargers and converters in a later video. How to connect the generator, inverter, battery charger, and converters will also be covered in a later video. A few safety warnings regarding using fuel-powered generators and inverters. Fuel-powered generators produce carbon monoxide. Generators must always be used outside, never inside, including the garage, even with doors and windows open. Carbon monoxide gas is a byproduct that is odorless, tasteless, with no smell to alert us. Buildup of carbon monoxide requires a fire department fan and equipment to remove. Opening windows and doors will not be effective. Do not leave gasoline next to the generator. Monitor the generator frequently and turn it off when not in use. Always have a battery-operated carbon monoxide detector when using a generator, even if the generator is outside. Any change in the wind could potentially send fumes back into your house via any open doors or windows. When filling the generator with gas, make sure to allow the unit to cool before filling. Gasoline is extremely flammable. Never place the generator near combustibles. Never plug a generator directly into home outlets. Generators should be wired in accordance with electrical code. Generators should be treated as you would any electrical appliance in terms of water. Make sure you're not standing in water when using it. Use of gasoline. Make sure it's stored in a UL approved container. Transport gasoline secured in a vehicle to avoid spillage. Do not transport in the passenger compartment. No smoking near any gasoline or gas cans. Fumes are flammable and explosive. When pouring gasoline, make sure that there is no spillage on the side of the container or around your work area. Here are signs and symptoms of carbon monoxide exposure. Carbon monoxide directly poisons the cells, especially the brain. Symptoms are variable related to the overall saturation and include 15 to 20% saturation, headaches, fatigue, confusion, 20 to 40% hallucination, combativeness, nausea, visual changes, 40 to 60% hallucination, combative, coma. Greater than 60% mortality rate of 50% or more. Seek medical attention immediately if symptoms appear. Now on to off-grid DC circuits. Let's discuss the DC circuits required to power our stuff. First, we'll deal with our DC loads. Remember, a load just equals the item you want to power. In previous videos, we discussed the different loads that we may want to power, both AC and DC. Now, in addition to the item to be powered, the load, we want to consider where our loads will be located, specifically in reference to the location of our battery pack and inverter. Starting with the location of the battery pack should ideally be inside the cabin, trailer, or van. That's if you're using lithium iron phosphate batteries. Other lithium chemistries and lead acid batteries should not be stored inside the living area. In general, batteries should be stored in a cool, dry, well-ventilated area near the electrical panel while ensuring it is protected from extreme temperatures and direct sunlight. Recall my previous comments regarding battery pack containment, including weight considerations for mobile applications in a previous video. Some additional factors to consider when choosing a location. Batteries perform best at moderate temperatures, so avoid placing them in areas prone to extreme heat or cold. Remember also, never charge lithium batteries at freezing or below. Choose a location that allows for easy access to the battery pack for maintenance and monitoring. If you place the battery pack outside, ensure it is housed in a weatherproof closure. A potential placement location is a well-ventilated closet near the electrical panel. In general, you want to protect the batteries from the elements as well as rodents, etc. Important considerations. Different battery types have specific placement requirements, so always consult manufacturer's instructions. Battery pack should be securely mounted, whether it's a stationary or mobile setup. Always follow all fire safety regulations and local building codes when installing and locating your battery pack. Next, determine your loads and the location of your loads, I mentioned earlier. Remember, this is not a how-to guide, but a big picture reference as to what you should be aware of. Safety first. If you don't know something, ask someone who does. You want to draw and use a schematic diagram as well as any supporting notes, and I've provided a sample schematic. Typically, you will have a separate circuit for each load. Consider the power requirements of the load and the distance from the battery pack. Using Joule's law and online guides, you can select the proper wire gauge and fuse size for the load based on the length of the circuit run. Remember our discussion on wiring in a previous video. For DC circuits, I recommend rated wire with the appropriate connectors on the ends. Battery pack should be switched on the positive side of the pack. The switch needs to be properly rated for the voltage and maximum current requirements of your setup. From the battery pack switch to the fuse block, the wire size is based on the total power requirements of the entire system. Here's some additional items to consider. You want to be systematic and methodical in your planning and execution. In general, start from the fuse block to the switch to the load and back to the shunt. That's your complete circuit. All of your DC loads must go through the shunt. The shunt should be located on the most negative point of the circuit. The shunt is what allows you to monitor the energy in and out of your battery pack. I recommend cable versus individual wires where appropriate. We went over this before, but remember, while the terms for wire and cable are often used interchangeably, technically, a wire is one electrical conductor and a cable is multiple connectors or a group of wires encased in a sheathing. Something else to consider is your load polarity specific. With DC circuits, there are items that are polarity specific, meaning that there's a positive and a negative. You want to make sure you hook it up correctly. Wiring an item improperly can damage the item and or blow a fuse. And always remember to use fuses. You want to secure the wiring. I also recommend labeling each cable run. You want to test the circuits as you go. Some items will be individually switched and some will be on all the time. For example, security cameras. Now in reference to this schematic, we'll make some observations and comments. Note that the battery pack is a 48-volt setup. Thus, the use of a DC to DC converter. The DC to DC converter takes the 48 volts from the battery pack and converts it to 12 volts so that we can operate all of our 12-volt load. The DC to DC converter used will be determined by the voltage requirements, both the input and output, as well as the total power output necessary. Starting with the battery pack, let's walk through the above schematic diagram. Positive side of the battery pack, we have our main disconnect switch. The switch needs to be able to handle the total current and capacity of the entire off-grid system, as I mentioned before. This allows us to completely disconnect the battery pack from the rest of the system. The main fuse is also sized based on the total capacity of the system. The component load with the greatest current draw will most likely be the inverter. The inverter should operate on 48 volts and be separately fused. The DC to DC converter should also be fused on the input side, which is not shown. The output of the DC to DC converter is distributed by the 12-volt fuse panel. In the fuse panel, 12 volts is provided to the individual loads. Some of the loads, such as lights and fans, will be switched, and some loads, like the pump shown on the schematic, are not individually switched but are always on. Please note, in an actual setup, I recommend switching the water pump. You don't want to have it on all the time. The negative side of the 12-volt loads will connect to the negative side of the DC to DC converter. The negative input side of the DC to DC converter, as well as the inverter input negative, connect to the shunt. So all the negatives will connect ultimately to the battery pack. As I mentioned, the DC to DC converter and the inverter, they all have to go through the shunt. If it doesn't go through the shunt, it's not being measured and we're not keeping track of that power in and out. All of the battery pack loads go through the shunt. The shunt is what is used to monitor the current flow in and out of our battery pack. A little more information on shunts. A shunt works on the principles of Ohm's law. Remember, E equals I times R, or voltage is equal to current times resistance. Basically, a shunt is a known resistance. Using a voltmeter, we measure the voltage drop across that known resistance. Here's an example of what I'm talking about. A shunt will be rated by the voltage at a certain current. A common shunt is a 50 millivolt at 500 amps. That means that when 500 amps passes through the shunt, the voltage measured across the shunt will be 50 millivolts. So there's a 50 millivolt voltage drop over that known resistance. A millivolt is 1,000 of a volt. To read the current, we simply scale our voltmeter to amps. Example, if you have 500 amps of current, the voltage drop across the shunt is 50 millivolts. The scale on our meter would be made to read at 500 amps instead of 50 millivolts. You get the picture? Technically reading millivolts, but we're going to scale it to read amps. It'll look like analog is reading. If you pass 250 amps through the shunt, the voltage drop is 25 millivolts. On the meter face, it would read 250 amps. 125 amps would be measured as 12.5 millivolts and would be labeled as 125 amps on our meter. It's linear. The shunt is a known resistance that produces a voltage drop when current passes through it. Using Ohm's law, we can calculate the value of that resistance, and the formula for resistance is equal to voltage divided by current. Using the shunt values of the above example, 50 millivolts divided by 500 amps gives us 0.00001 ohm. So you can see the amount of resistance is very small. The voltage drop across a shunt is usually between 50 millivolts and 100 millivolts at the rated. The output voltage from a shunt can be modified, converted to a digital signal before being used. The instrumentation to calculate watt hours uses a timer circuit. The system voltage as well as the shunt are used to calculate power over time to give you watt hours. Well, that's it for this video. Thank you for watching. Please leave any questions or comments below. And if you would, please like and subscribe. Hope to see you next time.